Imagine trying to fit a 130 gigabyte neural network into a 48 gigabyte graphics card without completely, breaking the model's brain.
Right. I mean, on paper, that just sounds like a total hardware impossibility.
It really does. And if you're tuning in late right now, maybe you've got your IDE open on one monitor, a cold cup of coffee on the desk, and you're just sitting there trying to figure out how independent developers are suddenly training these massive frontier class AI models on basically consumer hardware.
Yeah, it's a complete paradigm shift for the whole industry.
It is. So today, we are looking at the math and the architecture that actually makes that hardware impossibility a reality. Welcome to the deep dive. We are digging into the QLoRA breakthrough and how it essentially eliminated the multi-million-dollar server farm from the fine-tuning equation.
Yeah, it fundamentally rewrites the resource requirements for AI development.
Yeah.
We're looking at a methodology here that takes a 65 billion parameter model, right?
Huh.
Something that typically requires an entire cluster of A100 GPUs, and it just runs it and fine-tunes it on a single 48 gigabyte GPU.
Okay, let's unpack this, because I want to stop right there and just look at the raw math of that.
Okay.
Because for anyone who has ever dealt with memory management in software, this sounds like a typo.
It really does.
Let's look at a standard 65 billion parameter model. If you are loading that into memory in standard 16-bit precision, that's roughly 2 bytes per parameter.
Exactly.
So you are looking at 130 gigabytes of VRAM just to load the static weights into memory. Like, that doesn't even account for the context window, the activations, or anything else. It's literally just the resting state of the model.
Right, and if you want to actually train or fine-tune that model, the memory requirements just completely explode even further.
Oh, yeah.
Because when you run backpropagation, you aren't just storing those static weights. You have to store the optimizer states too.
Which is a massive overhead.
Huge overhead. Because if you're using something like the atom optimizer, it keeps a moving average of the gradients, right, and the variance for every single parameter.
Right.
And crucially, those optimizer states, they're usually kept in 32-bit floating point precision, just to maintain the mathematical stability during training.
So for a 65 billion parameter model, those 32-bit optimizer states add another 4 bytes per parameter.
Exactly.
That's another 260 gigabytes of VRAM. Just for that.
It adds up fast.
Then you add in the gradients, you add in the activation memory, which, scales up with your batch size and your sequence length, and you are easily pushing towards 700 or 800 gigabytes of required VRAM.
Yeah, you'd need something like 80 gigabyte A100 GPUs all linked up with NVLink, literally just to keep the training run from crashing with an out-of-memory error.
And that kind of hardware setup, that costs as much as a house.
Which is exactly why the open source community was basically locked out of the frontier model space for quite a while.
Yeah.
Like, you could download the weights of a massive model, sure.
Right, you just couldn't actually do anything with it.
Exactly.
Yeah.
But QLoRA changes this by attacking that massive memory footprint from 3 distinct angles. You've got 4-bit, NormalFloat quantization, low-rank adaptation, and paged optimizers.
And together, they basically crush that 800 gigabyte requirement down to less than 48 gigabytes.
Precisely.
So I want to start with the quantization piece first, because my internal skeptic is raising a massive red flag here.
Fair enough.
When you say we are going from 16-bit precision all the way down to 4-bit precision, you're talking about taking a parameter that can have tens of thousands of possible numeric values and crushing it down to exactly 16 possible values.
Yeah, just 16 bins.
But surely you lose some precision, right? You can't just compress 16 bits to 4 bits for free. Where is the penalty paid? How does that not just result in catastrophic data loss where the AI completely forgets how to, form a coherent sentence?
Well, you do pay a precision penalty, obviously. But what's fascinating here is that the brilliance of NormalFloat, or NF4, is that it ensures you don't pay that penalty where it actually matters.
Oh, interesting.
Because standard quantization, the kind that does break the model's brain, it takes the total range of your neural network weights, say from -1 to +1, and just chops it up into 16 evenly spaced buckets.
Right, but the actual data inside a trained neural network isn't evenly spaced at all. Like, if you plot the weights of a massive language model, they form a bell curve.
Yes, a normal distribution.
A normal distribution, yeah.
Yeah.
The vast majority of the weights are clustered incredibly close to zero, with just a few random outliers stretching out into the long tails.
Exactly. So if you use standard evenly spaced quantization, those buckets at the extreme edges of your range, they end up mostly empty.
Right, wasted space.
Yeah, and the buckets right in the middle, around 0, they get violently overstuffed. Thousands of highly nuanced, slightly different weights all get rounded to the exact same 4-bit value.
So you basically destroy the information density where 90% of the model's actual knowledge lives.
You do. And NF4 fixes this by entirely throwing away the idea of evenly spaced intervals.
So instead of slicing the numeric range evenly, it slices the probability distribution evenly.
That is exactly the mechanism, yes.
Right.
NF4 uses the inverse cumulative distribution function of the normal distribution.
That's a mouthful.
It is, but basically it just looks at the bell curve and creates 16 buckets spaced by percentiles. So this guarantees that every single 4-bit bucket holds the exact same number of weights.
Here's where it gets really interesting because that makes total sense from an engineering perspective. To me, it reminds me of variable byte rate encoding, like for audio files.
That's a great comparison.
Right, because instead of allocating a constant stream of bits across a whole song, VBR gives tons of data to the really complex, rich sections of the music that human ears can actually perceive, and it starves the silent or simple parts.
Exactly.
So NF4 is basically VBR for neural network weights. It gives you incredibly narrow, highly precise buckets right at zero where all the complex mathematical reasoning lives, and uses wider, less precise buckets at the tails where the outliers live.
And because it maps perfectly to the natural statistical distribution of the weights, the mathematical integrity of the model remains largely intact.
That's brilliant.
It is. But compressing the model is really only half the battle here. Because now you have a heavily compressed 4-bit representation of a 65 billion parameter model, and it's sitting comfortably in your GPU memory.
Right.
But you can't train it.
Because you can't run backpropagation into 4-bit discrete buckets.
Exactly.
The mathematical updates during gradient descent are microscopic. If you try to apply a tiny update to a 4-bit value, it's just going to round to zero. The model's weights would never actually change. The whole learning process would just completely stall out.
Precisely. You need high precision to accumulate those really tiny gradient updates. And this is where the LoRA part in QLoRA comes in, low-rank adaptation.
Right.
Instead of trying to update the 65 billion quantized weights, we just freeze them entirely. They become read-only.
Wow, okay.
We don't calculate gradients for them. We don't store optimizer states for them. That instantly deletes hundreds of gigabytes of VRAM requirements.
I really want to drill down on the term low rank here, because we throw around the phrase LoRA adapter in the software community a lot, like it's just a magic USB drive we plug into the side of a neural network.
Yeah, that's how people talk about it.
But what is the actual matrix math happening under the hood? How does an adapter actually inject new behavior without modifying the base weights?
Well, it relies on a principle called matrix factorization or rank decomposition. So let's say you have a massive weight matrix in the attention layer of your transformer model. Say it's a 10,000 by 10,000 matrix. That's 100 million parameters right there.
Right.
In traditional fine-tuning, you'd calculate a 10,000 by 10,000 matrix of updates to add to it.
Which is obviously memory prohibitive.
Right. But the researchers behind LoRA hypothesized that the actual change in weights during fine-tuning has an intrinsically low rank.
Meaning what exactly?
Meaning you don't actually need all 100 million parameters to represent the new concept the model is learning.
Oh, I see.
So instead of one massive matrix, LoRA introduces two tiny matrices and multiplies them together. You create one matrix that is 10,000 by, say, 8, and another matrix that is 8 by 10,000.
Wait, let me just do the math on that. 10,000 times 8 is 80,000. So two of those matrices is just 160,000 parameters.
Exactly.
Yes.
You multiply those two tiny matrices together, and they produce a 10,000 by 10,000 matrix of updates that you can then add to the base model.
Oh, wow.
But during training, you only have to calculate gradients and optimizer states for those 160,000 parameters instead of the full 100 million.
That's a 99.8% reduction in trainable parameters for that layer alone.
It's massive.
That is a phenomenal trick of linear algebra. So what does this all mean? To visualize this for the listener, it's basically like having a massive frozen encyclopedia. That's your 4-bit NF4 compressed base model.
Okay, yeah.
You can't rewrite the pages. But instead of trying to, you just slide a transparent sheet of paper over the pages, and you write your highly specific, full precision corrections on that transparency.
I love that.
And then when a user asks a question, the model looks at the frozen encyclopedia page, looks at the transparent sheet on top of it, adds the math together, and generates the output.
If we connect this to the bigger picture, that is a perfect visualization. The massive encyclopedia provides the generalized understanding of grammar, facts, and logic, all tightly compressed in VRAM. The transparent sheet, the LoRA adapter, acts as the hyper-specific steering wheel that directs that massive intelligence toward your specific task.
Whether you're, teaching it to write Python code or analyze legal contracts or respond like a specific persona.
Exactly. And because the adapter is so incredibly small, we can keep it in standard 16-bit or 32-bit full precision.
So there's no rounding error in the learning phase at all.
None.
Okay, that covers the weights and the gradients. But earlier, you mentioned that memory spikes don't just come from the parameters themselves.
Right.
Because during training, especially with long context windows, the activation memory can suddenly spike.
It can.
If we are running this on a single 48-gigabyte GPU and we hit a massive VRAM spike during a complex batch, why doesn't the whole process just crash with a CU day out of memory error? Like, how does QLoRA actually handle the physical hardware limits there?
That is the third pillar of the QLoRA paper, and it's honestly one that often gets overlooked. Paged optimizers. Even with NF4 and LoRA, VRAM is still pretty tight on a single GPU. So the researchers integrated NVIDIA's unified memory architecture directly into the optimizer.
Meaning it can page out to the system's regular RAM?
Yes. Think of exactly like standard OS memory paging, but specifically for GPU workloads.
Okay.
When the GPU VRAM hits its absolute limit during a forward or backward pass, the system automatically evicts the optimizer states from the GPU and pages them out to the much slower but much larger system CPU RAM.
Oh, that's clever.
It is. And then once the compute-heavy step is done and VRAM frees up again, it just pages the optimizer states right back into the GPU to apply the updates.
It's essentially an emergency pressure valve for memory.
Exactly.
I mean, it might slow down the training loop slightly while the data travels across the PCIe bus, but it guarantees the training run won't crash.
Yes.
Which is huge for a solo developer running a job overnight. You really don't want to wake up at 8 a.m. to find your training script died at 3 a.m. just because of a slightly too long sequence length.
No, you definitely do not. It creates a completely bulletproof training loop on consumer hardware.
Yeah.
But of course, the ultimate question for any software engineer is, does this Frankenstein architecture actually perform?
Right, because you've compressed the base model into 4-bit percentiles, you're learning through this tiny, low-rank mathematical bottleneck, and you're swapping memory back and forth to the CPU. Does a model trained this way actually produce usable, state-of-the-art results? Or is it just a really cool parlor trick? Which brings us to the Guanaco models. Because the QLoRA researchers didn't just publish the math, right? They proved it by training an entire family of models using this exact technique.
They did.
And the benchmark numbers on these models are staggering. They took a top-tier open-source base model, applied QLoRA, and fine-tuned it on a single GPU. The resulting Guanaco models hit 97 to 99% of ChatGPT's quality on the Vicuna benchmark.
It is an incredible data point. But we need to look at how they achieved that, because it wasn't just the architecture doing the heavy lifting.
Right.
Yeah, the secret sauce of the Guanaco models was actually the data set they used for the LoRA adapter. They didn't just scrape a billion random websites and throw it at the model. They used a data set called OAS-AST1 from the Open Assistant project.
Ah, okay. This is where we get into the whole data quality over data quantity argument. Why is the OAST1 dataset so special?
Because it is a highly curated, human-generated conversational data set. It's built on interaction trees.
What does that mean in practice?
It means it doesn't just show a prompt and a response. It maps out multi-turn conversations, showing the model how to actually follow instructions, how to refuse inappropriate requests gracefully, and how to maintain context over several exchanges.
Okay, yeah.
And here's the kicker. It contains only about 9,000 highly refined conversational samples.
Wait, only 9,000 samples?
Yeah.
That seems incredibly small. We are used to hearing about models trained on literally trillions of tokens.
And that is the true revelation of the Guanaco experiment. You just don't need billions of tokens for fine-tuning. Think about it. The 65 billion parameter base model, the frozen encyclopedia, it already knows the capital of France.
Yeah.
It already knows how to write a quicksort algorithm. It already knows the rules of grammar.
Right.
The fine-tuning phase isn't about teaching the model new facts. It's about stylistic and behavioral alignment. It's teaching the model how to interact as a helpful assistant.
So a few thousand examples of pristine, human-written dialogue are mathematically vastly more valuable to the LoRA adapter than millions of rows of low-quality, scraped internet text.
Exactly. When you feed high-quality data into the LoRA adapter, the model absorbs the stylistic alignment almost immediately.
Which makes sense.
That is why they were able to achieve that 99% of ChatGPT quality in just 24 hours of training time. The QLoRA architecture provided the efficient memory envelope, but the Oasis T1 dataset provided the dense, high-yield learning signal.
I really want that to sink in for the listener right now. A benchmark that compares a model against one of the most expensive proprietary AI systems in the world, built by a monolith tech company. And an open source model trained with a 4-bit frozen base and a low-rank adapter on just a few thousand high-quality human prompts practically matches it in 24 hours. On hardware, you could literally buy at a consumer electronics store or rent in the cloud for a couple of dollars an hour.
It completely validates the architecture.
It really does.
It proves that the 4-bit NF4 compression does not handicap the AI's reasoning or fluency. The normal distribution mapping protects those crucial weights perfectly.
Yeah.
It proves the matrix factorization of the LoRA adapter captures complex behavioral fine-tuning perfectly. The outputs are functionally indistinguishable from training a massive model the old, expensive, computationally heavy way.
It changes the entire calculus of what is actually possible for a small team.
Right.
Like, it takes the velvet rope away from the frontier class models.
Absolutely.
Because before this, if an open source research team released an amazing 65 billion parameter model, most developers just had to look at it through the glass.
Right. You couldn't do anything with it.
You couldn't run it. You certainly couldn't customize it unless you had a massive venture capital budget to pay for the compute. It was just a toy for the elite labs.
But QLoRA shattered that barrier. It democratized large model fine-tuning more than any other single technique we've seen so far. It has enabled researchers at smaller universities, lean startups, and weekend engineers to take absolute state-of-the-art AI and mold it to their exact use cases.
And for you, the software engineer listening to this deep dive right now, this means the barrier to entry is entirely gone. You now possess the conceptual toolkit to understand exactly how the hardware limits were bypassed.
Yeah, you do?
You know why the model's intelligence doesn't break during compression. It's because of the statistical elegance of NF4 mapping the percentiles of the weights.
Right.
You know how the model actually learns without running out of memory? Through the matrix decomposition of LoRA and the safety net of paged optimizers? You can take this knowledge, pull a massive open weight model tonight, apply QLoRA, and start building highly specialized tools right on your local machine. If you want to build a medical assistant trained on specific diagnostic literature, or a specialized code reviewer trained on your company's proprietary code base, the compute bottleneck is literally solved. All you need is high-quality data.
It sets the stage for a massive shift in how software is built, because QLoRA isn't the end of this optimization curve, It is just the starting gun.
Definitely.
As we've seen, it opened the door to parameter-efficient fine-tuning, and the entire developer community is currently rushing through it, finding even more aggressive ways to quantize and adapt these models.
The pace is blinding, honestly,
Yeah.
and it's putting the power back into the hands of the individual developer.
It really is. And it leaves us with an incredibly profound trajectory to consider, something for you to mull over as you get back to your code tonight. Well, if we can achieve 99% of top-tier conversational quality on a single consumer GPU in just 24 hours, merely by optimizing how we store weights and apply matrix factorization,
Yeah.
what happens when the underlying base architectures themselves become exponentially more efficient by default? We are pushing complex training out of the data center and onto the desktop right now.
That's a great point.
Are we rapidly approaching a future where fine-tuning frontier models happens locally, in real time, right on the edge devices in our pockets?